This is a 10-minute introduction to the study of the Platonic and Archimedean solids. These shapes were discovered more than 2,000 years ago, but research continues to make new and surprising discoveries about them. It may be already known, but it is the case that the two fundamental ratios of the human form, 1:1, and the golden ratio, are also found in these shapes, the cuboctahedron and the icosydodecahedron. A new resource for making these shapes and the housings which they fit inside is being provided by Tarquin Publishing, kindly, and the link to their website is going to be found beneath this video. Here is one of the solids, a cube, perhaps the most well-known of the Platonic solids. It has 6 faces, and it has 8 vertices, and the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It wasn't noticed until the 18th century by a brilliant mathematician called Euler, that if you add together the number of faces and the number of vertices, in this case 14, you'll get 2 more than the number of edges. And that relationship obtains with all the Platonic and Archimedean solids and all other polyhedra under certain conditions. It's called a solid, not because it's full of some material, but because it's 3-dimensional. And it's called a solid to distinguish it from a 2-dimensional shape, which is called a plane shape, such as a square. If we open it up, we can see another way of presenting the cube, and this is called properly called the excavated form of the cube. You can see the center of the cube now, and you can see the radii which are joining the center to the vertices. So there are 8 radii in there. And this way of presenting it allows you to quickly see the ratios of the cube. For instance, if that is a 1 and that is a 1, then by Pythagoras that is root 2 from that vertex to that vertex. That's a right-angled triangle. And if you're looking at the diameter of this shape, then you can say that side is root 2, that side is 1. So the length of the diagonal through the center is root 3, root 2 squared plus 1 squared, all square rooted, root 3. And that diameter is, of course, the diameter of a sphere, because each of these shapes has a circumsphere. That is, it fits exactly within a sphere that goes around it, and all the points of the vertices touch on the sphere, and that's true for all the other Platonic and Archimedean solids as well. So it's full of mathematics. We can also see 6 square-based pyramids inverted. So that's an inverted square-based pyramid. If you turn one of these over, you can see what you'd expect if you talked about a square-based pyramid. And you need 6 of these to fit together neatly with glue and a good deal of tender loving care. You can fit them together using the resource which is being provided by Tarquin. For instance, this is a sheet you can pop out the net and make the square-based pyramid. But there's one more point here. If you think of enlarging one of these square-based pyramids, so that here's a bigger one, which is similar in shape. If you imagine this getting bigger and bigger, extending the radii to infinity, you'll have an infinite square-based pyramid which will contain 1/6 of all of Euclidean space. So there's a cube and a few points about the cube. There are, of course, many other points. Now if we look at these, you can see the 5 Platonic solids. There's the tetrahedron, which is the basis of them all. It's got 4 faces and divides the whole of space into 4. if you have this one here, we've looked at it, it's the cube. It divides space into 6, this into 8, that's called the octahedron. This is the dodecahedron, divides space into 12, it's got 12 faces, each pentagonal. And the last of the Platonic solids is the icosahedron. In its housing, if we open it up, you can see here it is. It's got 20 faces, so it divides the whole of space into 20 if you enlarge the triangle-based pyramids, which make it. And it's made of equilateral triangles. All the Platonic solids have the same shape on each face, but the Archimedean solids can have more than one of these regular pentagons on its faces. How do you make this shape, which is a truncated tetrahedron, from the tetrahedron? Well, you divide this length into 3, exactly, mark that point, same on this edge and same on that edge. Then you can imagine that you can form a triangle there, and then that triangle will be the base of a triangle-based pyramid. And if you slice off that pyramid in a plane parallel to the base, then you will get this shape here. You'll get a truncated vertex here. And if you do the same to all 4 vertices, you'll obtain the truncated tetrahedron with its hexagonal face and its regular hexagonal based pyramids. This is the truncated cube. If you apply the same process to a cube, this is the truncated octahedron. This is the truncated dodecahedron. This face is decagonal. There are 10 sides to this face, 2 5s are 10. So it's got 12 of these decagon faces and 20 of the triangle faces. If you look at this one, it's the truncated icosahedron. It's got 32 faces, just like the truncated dodecahedron, and it's rather famous because it's the football shape. There's the pentagon surrounded by 5 hexagons. Also, we have these 2 shapes, the cube octahedron and the icosydodecahedron. Now, you make this one by joining the midpoints of either the cube or the octahedron, it doesn't matter. If you join the midpoints, and you can see you've got a square there inside the square. That's this one that you can see, that's the square, you can see the square face. And then if you've joined that point, and that point, you can lop off the vertex, and you're going to get the triangle-based pyramid or triangle face of the cube octahedron. Now, we won't go through this, but you can see that if you joined the centers of the edges of this octahedron, you'd have a triangle, and then if you lopped off the square-based pyramid, 1, 2, 3, 4, you'd get a square face. The exact same procedure can be applied to the dodecahedron and the icosahedron, and then that will give you the icosydodecahedron. As we mentioned in the beginning, there are interesting ratios in here. If you look at a sketch of the human form, the Vitruvian man, you can see that the width of your full arms from fingertip to fingertip is the same as your height. That's a 1-to-1 ratio. And for an adult person, to the correct level of accuracy, that's perfectly correct. And you can see that this is an equilateral triangle, so the edge length to the radius is 1-to-1. Here we have the golden ratio between the edge length and the radius, so that golden ratio appears in the human form. That is to say, if you take the distance from the top of your head to the navel, and multiply it by 1.618, or root 5 plus 1 over 2, you'll get the distance from your navel to the bottom of your feet. And if you multiply that length by the golden ratio, you'll get your full height. So it's a fact that these ratios in human form appear in the cuboctahedron and the icosydodecahedron. So that concludes the introduction. Thank you very much for your attention, and if you wish to make these shapes, then please visit the website of Tarquin, which has its link displayed below.